As we said in the previous video, if we analyze this different context in which the word Tisquino appears, we can make some kind of inference about what Tisquino is. We can even infer things that are not in these contexts. So the fact that you can drink it, the fact that it comes in a bottle, it makes you drunk, it's made out of corn, you can say that it's a liquid. So none of these sentences says that it's a liquid. But once you have made some inference about what kind of thing you're talking about, then you can make conclusions about other properties of the word, even if you have never seen it before. All right, so now technically, how are we going to do this? Like algorithmically, how are we going to work things out in a way that I can have this inference about a meaning, the meaning of a word that I have never seen before? So this is something that many philosophers and scientists mentioned before. So, for example, Wittgenstein said that the meaning of a word is in its true use in the language. So there is no actually intrinsic meaning to the word apart from how you use it in the language. Zillick Harris said something like oculist and eye doctor occur in almost the same environment. If A and B have almost identical environment, we say that they are synonyms. And the most famous one, I think, is this one, and I think you will see it in every paper that talks about, distributional semantics mostly, is Firth, who said in 57, you shall know a word by the company it keeps. All right? The way we're going to do this is that if we abstract things a little bit and look at words as symbols, and especially symbols that we don't recognize as humans, just to see how the whole thing works. And then I am going to make a matrix, right? So I want to know if this word here is very similar to this word here, okay? Now I have different symbols on the columns, and these numbers specify the co-occurrence of this guy with this other guy. So this tells me that these two appear together 115 times in some hypothetical corpus, okay? Versus 89 times for these pair of symbols, this and that, okay? Now, if I do this by choosing what kind of symbols I want to put in the columns and what kind of symbols I want to put in the rows, then I can do something very smart, and I can say, well, these numbers here, these frequencies, are actually a vector that represents now my symbol. See, now that's the tricky part here, or the most important, the key part, let's say, not the tricky, but the key part here, is that I am converting something that is a symbol that I know nothing about into a vector of values that I infer from a corpus that I suppose it's big enough that it represents, the whole language. Now, if I have this vector that represents this symbol, if I compute some kind of similarity in between those vectors, they tell me how similar they are. And this is the hypothesis, and then you have to go ahead and verify that. So if we use the numbers that we have here, we can see that the similarity between this symbol here and this symbol here is 0.961, which is higher than the similarity between this one and that one, which is 0.770. The reason is, you can see, for example, the co-occurrence of this symbol with this one is 84. Relatively to the other values is really, really high. Okay, it's higher than this one, it's higher than the second one, it's higher than all the others. Versus here, you see it's number 10. If you look at the other values, 10 is very low. So the co-occurrence of these two guys is much higher, even when you normalize, than the co-occurrence of these other two. This difference in how these symbols co-occur with these column symbols is what tells me which ones are similar and which ones are not. Okay, so now let's stop talking about unknown symbols that have no meaning for us, and let's look at words, things that we actually recognize and we can work with. All right. So what I'm going to do here is the following. This is the same table. If you flip it back and forth, you will see that it's the same numbers, same everything. Even this similarity measures are the same. What I'm doing is the following. So I'm going to choose a bunch of nouns. Knife, cat, dog, boat, cow, pig, berry. All right. And then I'm going to choose some verbs. And then I'm going to count the number of times that these verbs take this noun as an object. So how many times in some corpus, and it has to be a corpus where I can tell what is the object of each verb. So if I count in this corpus how many times knife is an object of the verb get, how many times is it an object of the word see, of the verb see, etc., etc. All right. Then excuse me, then we're going to end up with something similar to what we said before, which means that this vector here is going to be my representation of the word dog. Okay, and I can actually call this X dog. All right, and in the same way, now I can see whether dog is closer to cat than it is to knife. Okay, by computing some similarity in between these two vectors. This is the first thing that we recognize that you couldn't do with the one-hot representation. Remember that the one-hot vector, you couldn't see any similarity in between two vectors because, the index that takes 1 instead of 0 is just an arbitrary index that happened to take that value when you were building your vocabulary. Okay, so if we try to plot these things, so here we're going to take 2 dimensions, which is get and use. So if you go back here, get and use, and we're going to just ignore the others. And we're going to just suppose that for each one of these nouns, we only have these 2 columns, because if we have only these 2 columns, then we can represent them in a 2-dimensional figure. And then we can plot each one of these. So we have cat over here, we have dog, boat, and knife. All right. So you can see that the distance between dog and cat is very similar to the distance, or close enough to the distance between dog and boat, but dog and knife are very far from each other, which is the same thing as these numbers here. Okay. All right. So if what we are trying to say in this slide is that if we represent only using 2 dimensions, we use a Euclidean space. Then we can compute these distances that are going to tell us something about the similarity. All right. So this distance, which could be done in many ways, in this specific case, it is just a spatial distance in between these guys, right? So it's just a spatial distance between knife and dog. All right. And the lower the distance, the more similar are the words. Okay. But the problem here is that the reason why boat ends up being as similar to dog as cat is because if you can see, the frequency plays a very big role here. So if you looked at this corpus, you would find that dog happened in the corpus 2.7 times as cat. All right, these numbers here and the x and the y indices are not, or the counts of dog are not normalized. So what ends up being is that the raw value of frequencies play a big role in what is similar to what. And that is not a good thing. So here is a good solution to this. Instead of using a spatial distance, we're going to say, look, cat and dog fall in the same direction starting from the origin. They are more similar in direction than actually dog and boat, because in between dog and boat there is this angle here that is almost zero for the vectors of cat and dog. But at the same time, it is much smaller than this angle here of 54.3 degrees that happens to be between knife and dog. Okay? And our similarity has to reflect that. So what we're going to do is we're going to say we want something where the direction is more important than the location, because these count actually, the raw values of the count should not have a very high weight in saying what is similar. We need to normalize the length of the vectors, okay, for the same reason. And we want to use the angle alpha as the measure. Okay, so what we are going to do actually is we're going to use the cosine of these angles. And we're going to use the following measure. Okay, so you had the similarity or the cosine similarity in between x and y is a multiplication of x and y. All right, look at the dot product. And the dot product is always like a similarity measure, right? And then you're going to normalize by x and y. Okay? What you end up having is that it's a value where when it's 1, they are collinear and they are very similar, versus when you have a right angle of 90 degrees, the similarity will be 0. What I mean by that is that the closer the similarity to 0, the less two words are similar to each other. The closer it is to 1 means that the words are very similar semantically to each other from a distributional semantics viewpoint, because there are other types of semantics that we will see in the next sessions. All right, so that solves the problem of basing the distance on a spatial distance that actually takes the raw counts into consideration. In practice, in between parentheses, what some people do is that when they have the x's and the y's, which means that when they have this table here, okay, what they do is that they go actually and they normalize. So they take each of the rows and they don't normalize them using this. Then if you do that for the whole matrix, and we will talk about this a little bit more later, then when it comes to computing the similarity, all you have to do is the dot product. All right. Okay, we can talk about that more in class if you want. All right, so you end up here having something, this is, I think, DSM is distributional semantic models. What you end up having is that if you try to look what are the words that are most similar to the word school, you can get country, you can get church, you can get hospital, you can get house, you can get hotel, you can get industry. So see how distributional semantics, this is one example, you can see others, and you will see that, you know, when we say that two words are closer to each other, it does not really mean that it's going to be consistent or they're going to be similar to each other in a specific way. It just ends up grouping together words that that appear in similar contexts in your corpus. Okay, so that's why it ends up mixing things like church, hospital with industry or with party, which is similar to school in some ways that are different than the way that school is similar to church. Okay, something that you can do with this is that if you take each word and you do a nearest neighbor, then you can do hierarchical clustering, and then you can construct some semantic maps, and you can kind of build something that says that all of these is one cluster. This is one cluster with some error, chicken doesn't belong here, etc. All right, this is very useful in many ways. We can talk about the applications of this, that why would we want to have a clustering of these things, or maybe even hierarchical clustering. Okay, so now that we have talked about this, we have to see we'd like to talk in the next video about in what ways we can vary this thing, in what ways we can tweak it and make it work in different ways.